In part 2 of this segment, we are going to consider the same ball colliding with the wall, but instead of it bouncing off the wall, it is covered in Velcro and it sticks to the wall. It comes to a stop after 0.2 seconds. What is the momentum before, after, change in momentum, rate of change in momentum? We want to add the information to the PT graph, and then the numbers we get for each of these we want to put in this table below and have a vector diagram for the change in momentum. Whoa. So we want our initial momentum. So P0 equals mv. And the mass was 1.000, and we had a velocity of minus 6.0, so we have minus 6.0 kilogram meters per second. Same as it was before. The momentum afterward is mv, 1.000, but it came to a stop. So its momentum afterward is 0 kilogram meters per second. Now, if we want the delta P, which is m delta V, which is 1.000, and delta V is V minus V0, we have 0 minus a minus 6. The final velocity was 0, and it started with an initial velocity of minus 6. So we have 1.000 times 6, or 6.0 kilogram meters per second. Now, right off the bat, we might notice that that value is 1/2 as large. We had 12 when it bounced off the wall. It's 6 when it sticks. Let's do it the other way. Delta P equals P minus P0. The final was 0 minus a minus 6. Lo and behold, we get 6.0 kilogram meters per second. So now we can see and have confirmation that the change in momentum when it sticks is only 1/2 as much as when it bounces off. Next, so let's fill in our table. Okay, when it bounced, the initial momentum was minus 6. Afterward, it was plus 6. The change in momentum was 12. And the rate of change in momentum was 60. If it sticks, we saw the initial momentum was also minus 6, but afterward it was 0. The change in momentum was plus 6, half as much. What about the rate of change in momentum? Delta P over delta T is 6 divided by 0.20, which is 30 kilogram meter per second squared. Well, let's graph these. Started out with the same feature, but now we make the after curve red. After 0.2 seconds, the momentum is 0. So that's how those two graphs compare. This is the bounce, and this is the stick. We can see the change in momentum was twice as large. We can see the rate of change in momentum had to be a lot larger to bring about a bigger change in momentum in the same amount of time. So what does this mean now if someone took a ball and threw it at your forehead and it bounced off versus it sticking to you? Instead of this being a wall now, imagine someone's throwing a ball at you, hits you with it's coming at you with a certain speed, bounces off with the same speed, versus someone else throwing the same ball, but it sticks to your head. Which one is going to hurt more? The one that's going to hurt more is this one. This will hurt more. because our head is bringing about twice the change in momentum every second as if it stuck to us, if it occurred in the same amount of time. If it occurred in the same amount of time. So that's the table comparison, that's the graph. And lastly, we want to look at the vector diagram comparison. So let's do that. We have, so this is our previous, and let me block it in here for us. This is for bounce. And now let's do stick. Well, let's see. We had an initial momentum of, it's P, the final momentum, which is 0. Oh, that's P, plus a negative P0. Well, P0 is this. A negative P0 is this. So that means the resultant change of momentum is this, which is 6 kilogram meters per second. Smaller change in momentum, smaller rate of change in momentum. This one hurts, and this one hurts less. In fact, it hurts half as much. So what is this rate of change of momentum? Stay tuned.